Hello and welcome to yet another video of Cornerstones of Math. Today I've got this nice little geometry problem for you. The problem is, there exists triangle ABC satisfying the side length of BC is less than side length AB and AC. That is, BC is the shortest side of the triangle. For an arbitrary point P inside the triangle, prove that PA plus PB plus PC is less than AB plus AC. That is, the sum of distances from P to 3 vertices is less than the sum of length of two longer sides of triangle. Alright, now it's time for the proof, and the first step I'm going to take is this. Let us draw a line parallel to side BC, which also passes our arbitrary point P. Suppose this new line meets two sides AB and BC at points D and E respectively. Now this sudden parallel line seems quite random and out of nowhere, but if I may elaborate, it is given in the problem that BC is the side having the shortest length, so it is kind of a special side among three sides of the triangle. And I chose to draw a line parallel to that special side. With this setting, I am going to handle two terms on the left-hand side of the inequality we want to prove, PB and PC. It is obvious that length PB is less than length of PD plus length of DB. That is, this length is less than this length plus this length. Also, PC is less than PE plus EC. That is, this length is less than this length plus this length. So we have already obtained two inequalities. Obviously, we want to deal with this length PA next, but this is where the things get complicated. As for this third length PA, the inequality must be set up rather meticulously by the careful comparison between length of the line segments. And as for length PA, we want to compare with length AD or AE. But here's the problem. You see, in our problem, it is undetermined which length between AB and AC is longer. They can even have the same length. And the problem doesn't end even if we picked one specific relation, because even in the case of same length relation, we can have different cases depending on whether a certain angle is acute or obtuse. And you can notice that a certain angle being acute or obtuse may alter the length relation between certain line segments. For example, in this case where angle AED is obtuse, we always have length PA is greater than length AE, but if angle AED is acute, then PA becoming less than AE is possible on some occasions. Addressing these cases one by one and proving for each case is a tedious work, but actually we don't have to do that. Logically, it is sufficient to prove only for the case where AB is greater than or equal to AC. That is, we don't even need to handle this third case separately. And it makes sense because this third case is perfectly symmetric to the first case, hence the proof would be essentially the same, only being symmetrical and nothing new. Of course, at this point, you may have understood that different result in length comparison is possible, depending on certain angle is acute or obtuse. But the thing is, it doesn't matter, because that is not the main focus here. Instead, let us focus on comparing PA and AD and this angle ADE. Due to this newly introduced condition, we now have the complete comparison of side length of triangle ABC, which is AB is greater than or equal to AC, and AC is greater than BC. This means that we also have AD is greater than AE, which is greater than DE due to similarity. Therefore, as for their respective opposite angles, we have angle AED is greater than or equal to the angle opposite to AE is angle ADE, and this is greater than the angle opposite to side DE, which is angle DAE. This can be verified by many ways, for example, either by using the circumcircle of triangle ADE or by using the law of sines, so I am not going to explain in detail here. Anyway, the important conclusion from this is that angle ADE cannot be the sole largest interior angle of triangle ADE. This means that angle ADE cannot be the obtuse angle. Hence, it must be an acute angle. This is the important conclusion that I wanted to draw from this condition. And because of this acute angle property, we can guarantee that length PA is less than length AD. Let me emphasize this again. This inequality is guaranteed to be true because angle ADE is an acute angle. So now that we have obtained inequalities on PA, PB, and PC, we can add them up to obtain our desired expression. So we have PA plus PB plus PC is less than AD, then plus PD plus DB, then plus PE plus EC. Here, notice that AD plus DB, which is this plus this, is equal to AB, and PD plus PE, which is this plus this, is equal to DE. So we have AB plus DE plus EC. Here I have already explained that DE is the shortest side of the triangle ADE, which means that DE is less than this length AE. So we have less than AB plus AE plus EC. And notice that AE plus EC, which is this plus this, equals AC. So we have AB plus AC. And this concludes the proof. Again, for the other case where length AC is longer than AB, the proof is just symmetrical. And that's all for today's video. Thank you all for watching. Please don't forget to hit that like and subscribe buttons if you enjoyed this video, and I will see you in another video.